a dar el profesor Flatt en el tema de fabricación digital con hormigón. Una serie de palabras con respecto al profesor Flatt, y así le conocemos todos mejor. Bueno, pues es que él es doctor en Ciencias de Materiales, obtuvo su doctorado en la Escuela Politécnica de Lausanne, en Suiza. Después hizo un postdoc en la Universidad de Princeton y posteriormente volvió a Suiza a trabajar en Sika Technology, siendo la persona que lideraba proyectos en el tema de materiales inorgánicos. En el 2010 obtuvo una cátedra en la ETH, en la Escuela Politécnica de Zúrich, y desde entonces está allí en su grupo. El grupo se llama Física Química de Materiales de Construcción y ahí es pionero, bueno, pues de diversos proyectos, tanto en la temática de aditivos como de fabricación digital, como os presentará hoy. ¿Qué más decir? Bueno, que también es en esta temática, es vicedirector del Centro de Competencia Suiza de Fabricación Digital en Arquitectura. A lo largo de esta extensa carrera pues, ha recibido numerosos premios, algunos de ellos como Robert Lermit Medal y también Stefan Brunauer Award. Y desde este año es también editor jefe del Cement and Concrete Research. Es, por lo tanto, un honor, Robert, tenerte aquí en el instituto durante esta estancia, durante este periodo sabático, y es un honor trabajar nuevamente contigo y estamos todos pues, encantados de escucharte.
Muchas gracias, Marta. Es un placer de estar aquí. Voy a dar mi charla en inglés. Si hay preguntas, la puedo contestar después, o en inglés o en una mezcla de español franco-andaluz de Granada. Okay, so I'd like to tell you a bit about work that's been carrying on at the National Center for Competence in Research and Digital Fabrication in Switzerland. I will tell you a bit about the center. I'd like to put some emphasis on how important interdisciplinarity is in this field, on what the challenges are to make this sustainable, and also show you some large-scale demonstrators to give you a sense that this field is progressing fast and that it is really reaching large scales, and that we should think about what is going to happen in the real world sooner or later. However, first I thought that I would start with this quote that I see coming to the Institute on the wall, and I kind of like it and wonder what it means for digital fabrication. So what is the mission of the material in the age of digital fabrication? What resistance does it need? As I understand, the term of moldeadora is very important for concrete. How do you shape the material? So yeah, I guess it makes me think, and I'd like to share with you some views on what's going on in digital fabrication. So we already heard not so long ago here a talk on digital fabrication, extrusion printing focused. Digital fabrication, you will have heard many projects, is happening around the world in various forms and flavors. This graph from Professor Buswell and co-authors shows you how over time the number of projects is growing and is an indication of the very fast growth of the field. In Switzerland, we have the privilege to have acquired so-called National Center for Competence in Research funding from the Swiss National Science Foundation. If all goes well, this lasts a total of 12 years, and we are now in phase 2 in year 6. So we have another 6 years to go if all goes well. In phase 2, we have 22 professors involved. Paid by the project, we have 47 PhD students and 8 postdocs, plus 3 technicians. Then there's other projects that are not funded by the government, but connected in different forms with different sources of funding, adding roughly 20 PhD students and 6 associated researchers. There's also a Master of Advanced Study and a very intensive set of collaborations with industry. What you see here on the graph is the robotic fabrication lab of the Department of Architecture. You have these 2 gantry systems that move back and forth with telescopic elements that can go also left and right. And at the end of these, you have robotic arms. So the idea in this floor space of 600 square meters is to be able to test processes at a scale that is significant for construction and architecture. So this is a very important playground for this project, and one where a lot of the mischief happens in our research. I would also like to point out that the whole building has been designed by our colleagues in architecture. The top part has a very nice open space and set of offices for the Institute of Technology in Architecture. The roof is designed by my colleagues Kamatio Kohler to apply some design tools that they have developed. Importantly, it's been robotically built. It's the largest roof built robotically in the world. At least it was some years ago. I haven't heard if it's been surpassed since. And what was done is that these elements were basically prefabricated and then brought on site and assembled. During the construction process, there was some adjustments that were needed, and that basically needed a couple clicks to get everything straight, and the robot adapted and construction continued. Interesting anecdote, the company who bid to build the project robotically basically saved money in doing it, and with the savings they paid for the investment in acquiring the robotic setup, which they now use for other projects. So there's a number of anecdotes. There's a nice video I actually don't have the time to show, so I want to move on to the following question, is why are we investing so much in this? Here is a list of the different professors, different chairs involved, different disciplines: architecture, civil engineering, robotics, computer scientists, mechanical engineers, and within these there's many sub-disciplines. As an example, in civil engineering, we have structural engineers, we have colleagues from geomatics, we have colleagues specialized in life cycle assessment, and us doing materials. So very broad initiative, and the question is it worth to invest so much? And I would like to share with you a study, actually more than a study, I'll show you, from a colleague in architecture, Professor Schlüter, who has looked at how skyscrapers are built in an Asian context. And what you see on this graph is a cross-section of a typical skyscraper with a lot of space in between the floors, for example, for the ventilation, air conditioning, and pipes of all kinds, electricity. What my colleague realized is that if you change the design of this building to optimize heat exchanges, you look at having a better facade engineering, but also an integrated floor slab. Or we could call it also a smart slab, where much of this is essentially condensed into this floor. Then you put 3 floors, where today you put 2. So what does this mean in an urban context? That you increase your floor surface by 50% in a given building envelope. And now the argument is the following. Let us imagine that producing this floor is more complicated than doing this. It requires different manufacturing. It requires more care, some other process, and I don't want to discuss how it can really be done, but just bring the example that manufacturing this suddenly changes your floor surface by 50%, so that the cost of producing this is probably ridiculous with respect to the one of increasing the floor surface. And that is really about the notion I would like to bring through: think different, build different. In my opinion, digital fabrication will not make it big, just reducing fractions of percent of what we already do very efficiently, but looking for other ways to do things to create new margins in areas and approaches that are not possible currently. Now, just to show you that this is not just an academic exercise, a building has been constructed in Singapore according to these principles and functions properly. There are publications about this from my colleagues' group. So, along the line of think different, build different, we should think about building nevertheless safe, durable, eco-friendly, and cheap enough. Cheap enough is very important because currently, and this will be one of my arguments, cost structures prevent us from using less material and being more sustainable. So that if we attack the question of the cost of some structures, we will benefit the overall reduction in consumption of resources in the construction sector. So let us take a look at an ordinary construction site, pretty heavy-duty formwork. In ordinary sites, we talk about 50+% of the cost going into the formwork as compared to the total formwork plus concrete plus reinforcement. And if you go to a building like this one, the Rolex Learning Center at EPFL, my alma mater university, fantastic building, iconic character, very elegant also, but in such structures you have to essentially build them twice. First out of wood or some polymer as a formwork, and then you build the concrete structure on top, generating a lot of waste because you can't reuse the formwork as it's a unique case, and the cost goes up to 75%. Their cases it goes up to 90%. And now think that we don't only want to build things like the Rolex Learning Center, but we might want to think about structures, arches, branch structures, which are structurally extremely efficient and well known since antiquity, basically, of being very efficient, but that are not standard shape, that are efficient when they're adapted from case to case, that have some curvatures, and you don't have standard formwork. The cost of doing that is quite high because of these non-standard shapes, and non-standard here means not just aesthetic for the fun of it, or extravagant for the fun of it, but structurally informed to reduce material use. So, to go further in this argument, let's think about how the cost of a unit might look versus complexity. And the argument is that conventional construction might look something like this, while as digital fabrication would look something like this, with somewhere a break-even point beyond which digital fabrication becomes cost-effective. Research, in particular, has the objective to reduce the level of costs in digital fabrication. It's one of the objectives, one of the hopeful outcomes of this research. And by doing this, you shift the break-even point to the left, and you increase the range of structures that can be built cost-effectively. And again, what this means is that structurally informed buildings can be constructed cost-effectively using less material, and that is, I think, where a lot of focus should be put in digital fabrication. Now, we can also think about what this means in the future for the market in terms of volume versus complexity. Maybe it has some kind of shape like this, and it's going to reduce a bit and extend towards the complexity. Exactly how it looks, I have no clue. We've kind of drawn this by hand to explain the concept, that the distribution of volume versus complexity will change. And that's why we're doing research and development. So to give you a sense about what is happening in the field, I said there's many projects around the world that have a lot of press. This is one which has been built by the NCCR Digital Fabrication. It is in a larger complex. You see this platform building here. This is the nest at EMPA. It is designed to host different modules to demonstrate innovation in construction. People go in, they can live there for a period, they fill in forms, like it, don't like it, etc., give feedback, and then move out. The next guests coming, etc. So it's a living lab, so to say, a living feedback lab. And part of this was built robotically. So this is the first house to be built with a combination of multiple robotic steps, and where everything is, all the main elements are built robotically. So this is composed on the top of a timber frame, which is assembled robotically, and a new concept for a membrane facade, which is filled with translucent aerogel granules, which give it high thermal insulation in addition to translucency. Now, the part I want to discuss more today is the concrete elements. The bottom part is a double curved wall, which increases load-bearing capacity for a given mass of concrete. And this is produced with a process of mesh mold, where a robot creates a reinforcement cage with the shape requested, and this then gets filled with concrete. Then we have the facade, where the glass panels are carried by concrete mullions, and the only load they have to take is the wind load, and this wind load is not the same at each point in the facade. So, to follow the idea of structurally informed objects, each mullion has a different shape to better accommodate the local expected wind loads. And then we have a so-called smart slab. This is a concrete slab which is topologically optimized to use concrete only where it's really needed, with respect to an ordinary concrete slab that in standard practice in Switzerland would have been put here. We reduced the amount of concrete used by 65%. This is done using a sandbed printer to produce a mold, and then concrete is applied. I will show you some videos of the different processes and walk you through a bit the different steps. However, first I would like to play a short video where my colleague Professor Kohler, who initiated the project and led it, together with collaborator Konrad Gasser, is going to give you some insight into this fabrication of the DFAB house.
The DFAB house is actually the first time very different new building technologies come together in an inhabitable building. It's a very exciting milestone for architecture, for science, and a future digital building culture.
So this is the mesh mold project where the robot is cutting, bending, welding the rebars.
Next is the place where innovation starts, where we push new topics forward, like in this case, digital fabrication, thanks to a collaboration between academia and industry.
This is the smart slab that is topologically optimized. The printing of the formwork.
I think it's key that we were able to bring together so many different people from different backgrounds, both in research and in the industry, to build this project.
So I mentioned architects, civil engineers, roboticists, material scientists, computer scientists.
Regardless whether you're a researcher or a professional or a builder or an architect, we all leave this project with a changed perspective.
The technologies shown here in the DFAB house, they have multiple implications and advantages. The ecology is much better if we build with these new technologies. The economy changes. And lastly, what we can experience here, the architecture changes.
So this is a smart dynamic casting. It's a robotically controlled step-forming process with a movable formwork. Robotic assembly of the timber frame from above two floors.
There is a strong societal impact by these new technologies and by literally taking the research out of the lab into reality, into a built, inhabitable house. we actually provide something very important to society and to experience these changes and discuss it.
Okay, so that was the DFAB house. Now, one thing I would like to underline is that the feedback that EMPA receives from people going there, and that was my personal impression also, is there's something special. You feel some form of comfort, you feel something different, you feel quality of living space. It's not some kind of nerd, geeky patchwork of things where you have to spend half an hour giving them a discourse on why they should not be feeling the way they are, and they should be enjoying it rather than the opposite, right? It's something where afterwards you can tell the people that it's been fabricated digitally and the added value of that. But they feel a special experience going in there, and I think that is a big achievement from the colleagues involved in the design, who had to bring together what was available in the NCCR as methods, and then everybody made different compromises of what to do for the overall project. So I want to say a couple words now about mesh mold. I'll show these slides intermediate from the project. There's lots of people involved in what I'm presenting. So the main people here are Norman Hack and Katrin Döffler, who now respectively professors in TU Braunschweig and TU Munich. The mesh mold project, as I said, robotically you fabricate a mesh mold. A mold that you fill with the concrete. You saw that from the video. There's one very interesting anecdote to this project. At the moment we decided to go from, let's say, benchtop or toy experiments to wanting to do a building, then there's no excuse. You cannot leave the structural engineers aside. You have to calculate seriously. You have to make sure this is going to stand up. So discussing with them, and in first approximation, they said, listen, guys, it's very simple. In first approximation, you need a certain volume of steel within your volume of concrete. What this means, if you go through the back of the envelope calculation, is that the number of welding points depends on the diameter of the steel to the power 4, or inverse power 4. So we spent 1 year of 1 to 1.5 years, professional mechanical engineers and roboticists changing the tool head to be able not to work just with wires, but with rebars, not very thick ones, but still pretty decent ones. And this factor 3 means that there was a factor 81 in speed, because the speed is limited by the welding points. So this means that 1 year investment roughly increased the speed of the process by factor 100. And I think it's important to realize what this means in early stage developments. If in 1 year, by using the right specialists and not fiddling around yourselves, you can gain a factor 100, what does this mean for too early cost analysis? Of course, it's important to see where the market might go, what the opportunities are. It's important also in the discussion to think about where the margins of improvement can be, and not to immediately kill the project because you're a factor 100 too slow in this case. Okay. I have a couple of bits and pieces of the video here with the robot leaving the ETH. I should underline that the robot moves autonomously. There's some control still by the people, but it's positioning itself in space autonomously. It knows what to do, and that's the whole assembly. Okay, so I'll cut short on that video and just underline that we were very pleased. And you can see the researchers' smiles here, that they were very pleased to receive the Swiss Technology Award, competing with all other disciplines. So for construction sector, thumbs up. Now I'd like to talk about the process of binder jetting, which, as I mentioned, was applied to print molds that are then used for the smart slab. Binder jetting, as you know, is been in construction, really pushed forward by Enrico Dini, who's developed large-scale printers and made some very interesting contributions. I would like to underline also this bridge near here in Alcobendas that even attracts tourists. And also the level of resolution that you can get. This is a so-called digital grotesque by my colleagues from the from the Digital Building Technologies chair. It's presented at the Centre Pompidou in the exhibition Printing the World. And if you take a close-up, you realize the level of resolution that you can get. So this has been described as the world's highest resolution ever printed object. Now, you might say, why do we need this in construction? Now, in most cases, you don't need that level of resolution, but remember my example of the skyscraper. There might be things that other digital processes cannot do, and this one can. This one is quite labor intensive. You saw the guys in the video brushing off the sand that hasn't been printed. You don't want to use this for an ordinary thing, but if you've got overhangs, if you have cavities, it's probably unbeatable. The question is, when do you need those overhangs and cavities? Okay? And of course, for high resolution things like that, it's extremely unique. So, here's a little video on the smart slab. As I mentioned, it's been topologically optimized. There's a lot of interaction with the mesh mold project to do a coupled optimization of how the mesh mold wall would be and how to connect the smart slab. This is the process of printing in the sand, so squirting binder, removing what's not printed. Then you have to spray it with a compound to help remove the concrete afterwards. There were additional parts creating bark structure, also where the cables for the post-tensioning were going to be placed. And then fiber reinforced shotcrete being placed as first layer, and then you'll see the larger structures above. So a lot of work, but quite unique in capacities with respect to the other processes. So now I'd like to turn to something that started as smart dynamic casting, mainly with Ena Joret, Frici, and is gone into something that we now refer more generally to digital casting. I'd like to show you different ways in which this has been happening. This is an old video, and it's a process where we tried to see if it's possible to have a let's say square section going up and turning, and the concrete is basically prepared in a batch which is retarded with a compound, and then it's delivered here after adding an accelerator and incrementally in small amounts. Now the process is automated. You have the batch of retarded concrete getting pumped, the accelerator goes in, is mixed, and it's delivered in the formwork. The trick is that at the moment you release the material, it should be strong enough to carry what's in the formwork, but it should be soft enough to be shaped. And then over time, its strength should increase because the height of the concrete to carry, the pressure, the load, is increasing. So there's a lot of cool cement chemistry to do in that. I won't get into the details, but it's a process that we generally refer to as setting on demand, and I will show you how it can be used in other applications. This is how we were producing, in a slightly modified smart dynamic casting process, the mullions. So we put this in a frame, and we had an actuated formwork. So in this case, we are not twisting the shape, but we have something that deforms, and the concrete is being pumped goes in a mixer, comes up here, an accelerator is injected, it's mixed as the material flows upwards, and then it comes down a chute into here, and you'll see a little video to show you how this is working. So first, here you have the animation of the actuated formwork, which is changing in shape as it's going upwards. And you have a video camera mounted on the moving part following the deformation of the formwork as it's going upwards. Okay. Yeah, okay, whoops. So, yeah, that's how we've been working with smart dynamic casting, and the idea now is, well, wait a minute. If we can activate the concrete so that it sets relatively rapidly, what does this mean in terms of the hydrostatic pressure it can resist? What does it mean in terms of pressure on the formwork? Could we not use the technology to take formworks that are much less resistant, for example, that could be printed out of plastic with standard FDM process? And this is what I'm going to tell you about in this case. This is about 1.5 meter, a bit more, concrete element using standard reinforcement. As the previous process, the great advantage of digital casting is that you don't have to change the process of reinforcement. In my opinion, one of the big challenges for digital fabrication is to do reinforced concrete without changing both the process for the concrete and the process for the reinforcement. So here you have an example with a formwork which is printed and a reinforcement. This is basically then combined. And we're going to be placing the concrete inside of this. With ordinary concrete, it would burst relatively rapidly. But with the process of setting on demand, it's not the case. The concrete formulation is relatively standard, a bit adjusted, not too many courses, but it's perfectly okay norm-wise. The accelerators also, the reinforcement also. The formwork is the only thing that's really changing. So this is the object, and it is now standing as a pavilion at the entrance of the headquarters of Basler Hoffmann, a leading engineering company in Switzerland. This concrete trunk is carrying this robotically assembled wooden structure and is a demonstration that this process can be scaled. So say, okay, that's interesting. Now, the problem with printing this formwork, if you want to transport it, this plastic formwork, you might damage it. Or it takes a lot of time, and there's possibly other inconvenience about first printing and then using. So the idea is to try and print as we fill. Here's just an example first. If we print this formwork and we pour the concrete without accelerator, it bursts. What we're doing here is, as you see, going up and printing, and at the same time we're filling with something which is initially fluid but hardens very rapidly. So the idea now is, could we not have a process where the printing is going up and the concrete is going up at the same time? What's the advantage? The advantage is that the hardened concrete on the bottom stabilizes the formwork against buckling. Okay? And you don't have the problem of having to transport the formwork. You can print it really ultra thin. You save material. You go faster. You have all kinds of advantages. So what can be done with this? Well, there's been a master thesis project supervised by the group of groups working on that. You have the specific names of the people most involved here. And this is the process printing, and you will see that the concrete is then being added later in the video. Anyway, so let me move to the demonstration. The students went through different processes of designs and ultimately wanted to do something which I find looks kind of like a gremlins kind of shape. And for ordinary concrete, it's not necessarily something that's easy to produce with a mold. And they had, oh, something's wrong with the video here. This design process where There's basically these cavities here, which are aimed at passing cables so that the object is produced in 3 parts and then post-tensioned, because they wanted to check the possibility of post-tension. But we could have done it in one go. Okay, so here's the printing. The formwork goes ahead a bit, and the concrete catches up. And then this concept that you're progressing with the concrete and the formwork together to produce these shapes. So here is other parts, and this is the final object produced. Again, if you try to do this without setting on demand chemistry, no way. If you try to produce this shape with ordinary processes, possible but complex, you could sandbed print the formwork, but you would have much work to remove all the sand and etc. So there are many processes. They have their advantages and limitations, and it's a question about knowing which process is best for which application. I think that is another important thing I would like to bring through as message today, is that digital fabrication is not just extrusion of concrete. So let's go further and come to this idea of structurally informed objects. And remember that folded structures are very efficient ones to increase bending stiffness, for example. Here is a case where we've done smart dynamic casting with a plexiglass mold so we can see what's going on, which is then being slipped and following an unconventional curved trajectory to make it a bit more challenging. This is possible, but not robust. It's really delicate to get the material to behave as you want it to behave, because the friction forces are very high. We've analyzed this. We have a nice mechanical early state analysis of what's involved, of what the operation window is, so we understand in terms of material properties what's the limitations. Therefore, the question is, okay, moving this produces a lot of friction. Could we not make a folded formwork that's static but very cheap to produce? So the cheapest idea is just go to the market and buy a roll of plastic like this, and then use setting on demand to fill it with concrete. So this is a bit thick plastic, but you shake it around, it's going to bend in all directions. And essentially with this process, you can see the robotic filling is working and there's barely any deformation of this just plastic foil. That starts to be what I call cheap formwork. Okay. Of course, you can't do any shape with it, and there's other processes that can help you when you need to go to more complex shapes. Then concrete extrusion. A lot of groups are working on this. I think it's an exciting subject. I think that there's been a tendency to see this driven by technologists who haven't initially thought so much about what to do with it. And for us, it was interesting then to support the work of my colleague Dillenburger, who came with more of a vision on how to use it from an architectural point of view. And this is, oops. Oh yeah, so I'm going to go into concrete extrusion. A quick acknowledgement to the main people involved. Anna Anton is really the leader on this, and Lex Reiter has been doing the material development for it, and many other people doing other important contributions. So here's the printing. You can notice that in this case we're using material which is very fluid initially, but hardens very rapidly. There's a mixing chamber on the top of, just before the nozzle where the accelerator is added. And now we're capable of going vertically at more than 1 meter per hour, even up to 5, I think, but extremely fast. That's the challenging part, because you have the load going up and it's in relation to the rate at which the concrete is being hardened. If you're going for a much larger contour length, then you don't need to be as drastic on the material, and you can look for other types of performances. So there's different papers that we've published, and there's quite a lot of work on concrete extrusion. In this case, I just wanted to show off the work by my colleague Dillenburger for this dance festival in the Alps. These are columns that were requested for a stage demonstration. What is important is that this is a demonstration to prove that we can do it before getting a project for a 24-meter tower, which is now granted and in the works. And the same guy doing the design of this and of the digital grotesque is doing the design of the tower, so I think it's going to be quite exciting to work with him on concrete extrusion. I can't talk about concrete extrusion without recognizing the pioneering contribution by Professor Koshneris at the University of Southern California, and how many years ago, more than 20 years ago, he really had a vision and has had a pioneering role for the field. I think it's also very important to recognize how the company Winsun in China stirred up a lot of attention around the world in the press. Sometimes maybe some statements were a bit overdone in the press, but I think it really got people to wake up. Their claim of building 10 houses in 24 days, not sure we all wish to have that as a house. It's not the greatest design, but it's a proof which has really had a huge impact in the field, and I think should be recognized for that at least, if not more. Then I think importantly also is the work done at TU Eindhoven, where they really look at the mechanics, the structural mechanics, in a way that has not been done by other groups, to my knowledge, or scale that has been not been done. This is a bicycle bridge that has been built there in the process of building these houses. Excuse me. And I wanted to underline that they are organizing the next conference, Digital Concrete 2020, in July, and in principle one of these should be possible to visit. So in case you're interested, check out Digital Concrete 2020. So, what are the requirements for concrete to be processed in either digital casting or concrete extrusion? There's a number of common points, but quantitative differences in the requirements. So it has to be pumpable. This typically means use less coarse aggregates. It increases the paste volume. It makes the performance in terms of sustainability worse. There's no question about that. But you can save then in terms of how much concrete is needed. The concrete has to be placed. It should be what we refer to as placeable. Then it has to develop enough strength for the building rate to be sufficient. People talk about buildability, and achieving structural scale heights in fast processing times requires hydration control. And meeting all these requirements requires chemical admixtures and control of hydration chemistry, which made it for me a fun subject to get into. On a conceptual level, we can think about this as such. Here would be reported strength, shear strength, compressive strength. I prefer to report it as a number of layers that the bottom layer can carry. So initially it carries itself, and as time goes by, after a certain time, it has to be able to carry 2 layers, sometime later 3, etc. Now the strength of the concrete would typically increase initially to some level, plateau off, and then later, when the C3S really starts to hydrate, it will increase more. So in many cases in extrusion printing, what you will see is that there's a shade between the first 50 to 70 centimeters and the next 50 to 70 centimeters and the next 50 to 70 centimeters. That's because they're not controlling well this open time, and they have to wait, because if they continue, it collapses. There's progress. It can be controlled. Not everybody controls it, and it's an issue. So this is, on a very conceptual way, the factors that one should. This is an example of a structure collapsing. So you go up a little bit too much load, and then it falls down. And very clearly, what you don't want in industry is one day for this to work, another day for it to work, and then it doesn't work, and you don't know why. Etc. So robustness is more critical because the operation window is more critical than in ordinary concrete fabrication. The exciting part for material scientists is that we're needed, right? The bad news for the industry is that they have to pay specialists. Okay? Anyway, so this is about set control. We can look at it in this form also, yield stress and time again, where there's a region where the strength is not growing fast enough. There's a region where it's too fast, and then you would have layering. Again, there's different publications about this. If you're interested, there's some references. If not, I can point you to them. Summarizing, notions of pumping are crucial in most processes of digital fabrication, placing also, and building, and they have their nuances, which in the end mean that a material which is good for this process has to be changed a bit for this one, and vice versa. Okay, now I would like to move from having discussed at one point the printing of formwork to thinking, how could we now think of maybe almost integrating the formwork with the concrete, or looking at other cost-effective ways of producing complex structures in formwork. This is linked to a project called Knitcrete, and high-low is actually a demonstrator. It would be rather cable net that should appear. The key people here are Mariana Popescu and the late Matthias Redner. Here's Mariana in front of an industrial knitting machine that we have at ETH. And the idea in her project, what about knitting the concrete formwork? And then you stretch it somehow, and you apply the concrete. If you do that, it's going to be too weak, so you need to stiffen it, and we do that by spraying a grout, which hardens rapidly. And then if the hardened textile has a load-bearing capacity, you can add concrete to it, and you've got an ultra-cheap formwork for complex geometries. So here's a video of the process for a demonstrator called Knit Candela. This is at ETH. The students knitted this textile 36 hours. They went to Mexico. It was a homage to Felix Candela, pavilion. And then it's stretched. Craftsmen applying fiber reinforced concrete for this pavilion in a project by the Block Research Group and Zaha Hadid Architects, where from the side of my group we were helping with the spraying of the fast-setting grout. This has been a blockbuster in terms of awards in the field of architecture or nominations and etc. So I won't go through it, but just mention that it's received a lot of attention and recognition, and we think that it has a huge potential. Again, not for everything, but it very clearly delivers the possibility to build cheap formwork for more complex structures and structurally informed shapes. The key people here are clearly Mariana and Professor Block, but I also want to underline Lex's passionate contribution to the project in the aspect of cement hydration control. As I'm coming from that field, I like to underline it also. Now, the Block Research Group has also looked at another way to produce complex structures. Here, a shell structure for the high-low, another part of the nest building at EMPA. And the idea here is to prepare a network of cables which gets stretched, and you put a textile on top of it. And then you add the concrete. There can be some reinforcement which is added. They have some meshes of various polymer-based reinforcement systems, and some fiber reinforcement also, I believe. This is the rehearsal in the robotic fabrication lab, a 1-to-1 scale for this structure which is to be built, I think it's going to be next year, at EMPA. The thickness of this shell with respect to the length is 3 times thinner than an egg shell. So that's what my colleague Bloch calls saving material and structurally informed. So again, this message, let's think about using less material thanks to digital fabrication. I'm sorry, I have an acknowledgement slide of many people from the Bloch research group in particular involved in this, but I didn't paste it apparently in the right place in this file. So in case the colleagues see the video, it will be in the next presentation. I would at this stage also like to repeat that the Digital Concrete 2020 conference is being held at TU Eindhoven. Abstract deadlines passed. I think it's going to be an exciting event, so please check it out. The first such conference we organized at ETH Zurich in 2018. There are proceedings to the conference, and I would also like to underline that there was a special issue in cement and concrete research where there was a collection of keynotes and invited papers really aimed at covering the different disciplines needed when going into the field of digital fabrication with concrete. And the 2020 Digital Concrete Conference will also have a special issue in CCR, again, with a set of papers that should provide an overview on the important disciplines and the state-of-the-art insight into how to use that knowledge in digital fabrication with concrete. So to summarize, there are questions in this field that mainly require rheology control. This, from our perspective, is more of giving some consulting, some advice. There's no real research question or much beyond state-of-the-art contributions. It's important to be able to give it because it enables a lot of things. On the other hand, there are processes that require both and simultaneously a control of the rheology and the hydration, and that is much more challenging. That is where we have our research going on, where other groups also have ongoing research, and where I think that the key for these processes to become effective in practice and robust really lies. So in conclusion, I would say that a new digital building culture is on the rise, characterized by strong interdisciplinarity. Digital fabrication is part of it. It can improve the quality of the living environment. It must be used to reduce the use of natural resources. In respect to the environment, I think that if well conceived, digital fabrication can save resources, but it could also make it much worse if you do it badly, with a bad design, a bad material control, etc., etc. The concrete itself has a higher footprint because it's got less coarse aggregates. That's simple. You have to compensate for that, and you have to compensate for that in a robust way, and that's where technology is needed. I think the subject is fun and inspiring. I think it helps to move the whole field of construction and concrete construction forward. It attracts talented and motivated students. And I think that similarly as self-compacting concrete, fiber-reinforced concrete, and ultra-high performance concrete in the past have done, it helps to train people in the basics of concrete technology, cement science, and so forth, and brings them into the field as fresh talents to move the whole discipline forward. The NCCR, as I mentioned, is an ensemble of many people. There's about 100 researchers combining everybody involved. This is a group photo, and I clearly am here to give a presentation of the combined work of many people, of many groups. I hope that this is not misunderstood. I'd like to acknowledge in particular my two colleagues, Professors Gramazio and Kohler, who are pioneers in the field. They founded the first chair in architecture for robotic fabrication, and many universities followed since, they've also been very instrumental in getting people interested in the field, in pulling people in to contribute to this field. And for myself, it convinced me to look also at more applied questions rather than the more fundamental science I was working on in terms of rheology and hydration control. How does the molecular structure engineering of admixtures affect hydration kinetics and rheology and so forth. So while I still greatly enjoy this and try to push the boundaries of the science there, it's nice that this feeds back into the questions of material control for digital fabrication. So with this, I would like first to thank the Swiss National Science Foundation for their huge financial support to this NCCR, and to thank you for your attention while reminding you about the upcoming conference in case this has motivated you and raised a bit of curiosity for the field. Thank you for your attention.
Thank you, Robert, for such inspiring talk. It was really good. And now we have time for questions. If you, okay, 1 second.
Okay, thank you, Robert, for it was a wonderful and impressive the talk, of course. And of course, what was important is to see this group or this big team that makes possible all these advances and give us the idea that the 3D is a reality, no? And but in the group, you commented that there were some people doing life cycle analysis. Yeah. Could you summarize what is their impression?
Yeah, so, well, they have a plot which I kind of showed where you have this cost versus complexity sketch, and you could put life cycle analysis versus complexity also. So for a straight wall, personally, I'm not very interested, and I think it's going to be tough to beat building simple straight walls. Certainly, the level of improvement you need to achieve and performance enhancement is much higher than if you go to something that has a bit less of a standard shape. So the key element of their conclusions is it depends a lot on the level of complexity that you're looking at, and depending on that, you have this break-even point. So there are some nice publications. There's also a PhD thesis in the group of Guillaume Aber that can be looked up, and they're continuing in this new phase to now more specifically critically analyze the different projects to give feedback at an early stage of where possible penalties in terms of life cycle assessment may lie.
Thank you very much, Robert, for your presentation, your talk. Very, very, very nice and very exciting for the new research. Probably in a very sample question, but what is the key materials in this digital concrete? The chemical admixtures are the key material? Or there are other?
The combination of rheology control admixtures and hydration control admixtures.
They are the key.
Yeah, because ultimately, then the whole mix design, as for any concrete, is also important. Okay, but the key part is really to get the material to have the properties it should at the time it should, and you don't have the luxury of having a stiff, rigid formwork to hold up the thing in case it sets a bit slower than usual, you know. And from that point, that's, in my opinion, the make or kill of the process, of many process, of many approaches. In the case for the smart slab, the shotcreting, of course, you have to adjust it, but they're not shotcreting a very thick layer. For that type of shotcrete, you don't really need an accelerator. The initial flocculation is enough. So that's easier to control in a robust way. As soon as you go up and you have added load and nothing to hold it back, then it becomes more delicate. I should add also that, in my opinion, there's a big question with extrusion printing about the interlayer spacing. There's a lot of research going on and discussions. Is it problematic or not? Does the strength change? Does the durability change? And you have some answers which are yes and no, and what the reality is, it depends on the processing conditions. In particular, when you've deposited a layer, if that has a bit too much time to dry, then the connection can be much worse. It dries just a little bit. It seems that it's better because you have a bit of suction that helps the adhesion. But in the tower I showed you, what do you think the print contour length is? Anybody have an idea of the printed length for that 2.7 meter column? 2 kilometers. 2 kilometers of contour length, where you have to guarantee, if it's exposed to chlorides, that there's not one zone which has got a bit of a defect and allows the chlorides to go in faster. So from my perspective, that's a big challenge. If you're printing, again, this is what I tend to think, with something which is a bit softer, it's going to reduce the risk because the combination is easier. Produce with something softer, you have to print more layers because it can't be printed in thick layers. And yeah, so it's a long discussion, but I think there's a number of open questions. One consequence at present is that many people are thinking of printing concrete as a formwork, as a lost formwork, for casting concrete inside of it afterwards. And the key question there is the printed formwork, can you count it or not as a cover layer? Or can you count a fraction? So my kind of cynical approach to that, having been working now with civil engineers over some time, is that sooner or later they'll say, okay, you can count half the thickness. Okay, but I think until you can count the whole thickness as cover layer, that's going to take time.
Thank you very much and congratulations for your presentation. It's very, very impressive. My question is very simple. It's about all the materials. Have you tried with all the materials of other construction materials, metal, ceramic, gypsum, limes, etc.?
Yeah, so there has been a bit of preliminary work with gypsum, and it works. With ceramics, I'll get back to ceramics afterwards. With geopolymers, people are looking at it. There's a bit of work at ETH, but it's not the main focus. And we are looking at earthen construction, so printing earth also. But that is also kind of an exploratory small-scale phase. Our big focus has been with concrete, but we're also working, as you saw, with timber. So the NCCR's key focuses currently are concrete and timber. There was a fun work done with clay, where my colleagues have what they call remote material deposition. So they were shooting blocks of clay about this big, 20 meters away, and building a structure like that, and using the impact force to have an adhesion between the clay elements. So I'd say it's a bit more for fun. There could be options where rethinking that process might be of interest, but it's not a core thing that we're looking at.
Yes, this question is because one of the key is to build light construction,
yeah.
And it's very difficult to make light concrete and be able to pump this concrete.
Right. So we haven't specifically looked at that. I think that, yeah, so we haven't looked at it. I think it would have to be, what would be an interesting approach is first to look at the type of structure that would really make sense having a certain shape complexity to be built in lightweight, and then think about which process is most adequate. But we haven't specifically looked at lightweight concrete per se.
Thank you very much.
Yeah, thank you, Robert. Once again, I would like to insist in this case of materials. I had the opportunity to visit Enrico Dini workshop in Italy a few years ago, and he was using, you know, the 3D printing, and he was working a long time with magnesium cement. So my feeling is that the different alternatives you have shown to us today could need different materials to be optimized in the future. So what do you think about this? So you think we will have some type of universal material in the future for digital concrete, or we will have to use different type of materials depending on
Right. Let me leave a bit aside the sandbed printing initiative, because I think this has got its range of potential applications. The other things I presented, they're all done with ordinary cement, ordinary sand, ordinary aggregates, commercial admixtures, and etc. So it's possible to do it with what's available. Now, when there might be such an important market that one would start to produce materials specifically for that, I think we're a long way from that. So for now, we've really emphasized on using what's available commercially on a large scale. There's a fair amount of interest in trying to do digital fabrication with, let's say, geopolymer type things. So I will speak beyond the area of my competence to a specialist, but I think that there is an interesting aspect which is linked to health and safety. So if you imagine that you're adding the activator through a robotically controlled process, you're kind of pushing the humans a bit farther away from what many people present as a health and safety issue. And you potentially don't have so much of a problem in open time. And what in some cases might have been a problem for some materials could become an advantage and create new opportunities. So yes, there can be special needs, but with a bit of formulation know-how, you can do it with what's around. Now, the sandbed printing one is more delicate, I think. I probably will disagree with Enrico in terms of how much market this really has or what the applications are. I see it with a big potential for complex formwork, as we showed there. To directly be printing with the cement seems to be rather tricky. And I think we should, for large scale, stay away from the magnesium sorrel type cements you mentioned. I know that he's been working on that, but I don't have information on the details. I know that it's not that trivial because we're looking at it a little bit, and it's still work in progress.
You know, this bridge you have shown to us in Alcobendas was made by Acciona in collaboration with Enrico Dini. Well, the main problem with sorrel cement is the cost.
Yes.
It's quite expensive, but it works a lot.
Yeah.
It works quite good for this type of...
So what I recently told an audience of Italians, right? I said that innovation sometimes needs an Italian with a brilliant idea and Spanish who finance it. And then I referred to Columbus, and I said, don't let the Spanish once again take your good ideas and make a fortune out of it. Anyway, this is just an anecdote.
not, I think we can finish this. This seminar. Thanks to everybody for attending, and thank you, Robert, once more for coming on.
And thanks for
so
hosting
much.
me on my sabbatical.
Okay.